Hello friends, welcome you all to the 12th lectures on function analysis and its applications. In this lecture, we will discuss the LP spaces as Banach spaces. Following is the content of today's lecture. The LP spaces as Banach spaces. The LP spaces. Let P be a positive real number and let X be an arbitrary measure space with measure mu. Let f be a continuous complex valued measurable function defined mu almost everywhere on X such that integral over X mod f power p d mu is less than infinity. That is, mod f power p is integrable. We then say that f belonging to LP and define the symbol norm Fp by norm Fp is equal to integral over x mod xp d mu whole power 1 by p. We call norm Fp the LP norm of f or simply a norm of f. Now, our aim is to prove that the LP are Banach spaces. Theorem. The LP is a linear space under the operations f plus g x equal to fx plus gx. And if a be any scalar, then a of x equal to a into fx. Proof. Since members of LP are complex valued function and only suffices to prove that the LP is closed under these operations, that is fg belonging to LP and a is any scalar, this implies that f plus g belonging to LP and af belonging to LP. Okay? If fg belonging to LP, then integral over x mod fx power p d mu less than infinity, that is integrable. And also g belonging to LP, that is integral over x mod gx power p d mu less than infinity. Here we have taken f and g belonging to LP. Then to check f plus g belonging to LP, we have to check integral over x mod f plus g x power p d mu bounded. Okay, so let us prove it. First, mod f plus g x power p, it can be written as mod fx plus gx power p as per this operation. Okay, this is less or equal to mod fx plus mod gx whole power p. This is also can be written as less or equal to 2 maximum fx gx power p, that is 2 to the power p into max fx gx power p. Therefore, less or equal to this less or equal to mod fx power p plus mod gx power p. We can write, because this is the max value of fx and gx, any one we can take. So if we add any another function, that is greater. Okay, so this term less or equal to this term. Now integrating both sides with measure mu, this. Okay, So integral over x mod f plus g x power p d mu less or equal to integral 2 to the power p mod fx power p plus mod gx power p d mu. That is this one 2 to the power p mod fx power p d mu plus 2 to the power p integral mod gx power p d mu. Okay, both integral bounded. Okay, because f and g belonging to LP and we have this condition. Then both integral bounded, that is less than infinity. So we can say that f plus g belonging to LP. Similarly, for scalar multiplication, suppose a be any scalar, then integral over x mod af x power p d mu equal to integral over x a into fx power p d mu. We can write by this property. So this integral also can be written as integral over x mod a power p mod fx power p, okay, d mu equal to a to the power p integral over x mod fx power p d mu by equation 1. So by 1 this integral less than infinity. Okay, so that is any constant value multiplied with a to the power p, that is also constant, it means less than infinity. That is integral over x a fx power p d mu less than infinity. So we can say that a f is the element of LP. Theorem. Now we prove LP is a normed linear space. Okay, here vector addition and scalar multiplication are satisfied, so we can prove easily the other property of vector space or linear space. Okay, so we can avoid to give the detailed proof of other properties here. Now we prove the LP space or normed linear space. Proof. We verify all the conditions for normed linear spaces. Since norm Fp defined by integral over x mod fx power p d mu whole power 1 by p, okay, we know that modulus value always non-negative, that is greater or equal to 0. So norm Fp depends on the modulus of fx. Okay, so integral over x mod fx power p d mu whole power 1 by p greater or equal to 0. So first condition, norm f greater or equal to 0 satisfied. Second condition, norm Fp is equal to 0. So norm Fp defined as integral over x mod fx power p d mu power 1 by p equal to 0 as per the definition. Okay, so here taking the pth power of both sides, that is integral over x mod fx power p d mu equal to 0. Okay, here integral of mod value of fx power p. Okay, so we have only one condition, mod fx power p is equal to 0, that is mod fx is equal to 0. It means fx is equal to 0, that is f is 0 function. So norm of Fp is equal to 0 if and only if f is equal to 0. that is zero function. Second condition of norm also satisfied here. Third, if A be any scalar, then norm AFP equal to, as per the statement, integral x mod AF x power p d mu whole power 1 by p. It can be written as integral over x mod a to the power p into mod fx power p d mu whole power 1 by p. That is a to the power p whole power 1 by p, that is mod a into integral over x mod fx power p d mu whole power 1 by p. Again, this can be written as norm fp. Therefore, norm AFP equal to mod A norm FP. So, third condition also satisfied here. To establish the triangular inequality, we demonstrate the Minkowski inequality, which states the following: let Fg belonging to LP, where P lies between 1 to infinity, then norm F plus G, P less or equal to norm Fp plus norm Gp. Okay. The proof of this result follows as a similar approach to the one presented in lecture 2 for discrete presentation. Okay. So, it is omitted here. So, as per that pattern, we can prove it for this integral sign easily. Unfortunately, the norm for the LP space does not satisfy the condition norm Fp equal to 0 if and only if F is equal to 0. Okay. So, not always this condition satisfied. So, instead it satisfies the weaker condition norm Fp is equal to 0 if and only if F is equal to 0 almost everywhere. Here the symbol 0 cap stands for the 0 function. Hence, LP space are nonlinear spaces. Next theorem. For 1 less or equal to p less than infinity, that is p belonging to 1 to infinity, the LP spaces is complete. We have to prove here LP is a complete space. So, already we have proved here LP is a nonlinear space. So, now we have to prove LP is complete. Okay. Proof. Let Fn be a Cauchy sequence in LP to show that this sequence converges to a function f. For this purpose, first of all, we construct a subsequence of this sequence which converges almost everywhere on X. Okay, let us prove. Since Fn is a Cauchy sequence, for epsilon equal to half, there exists a positive integer n1 such that nm greater or equal to n1. This implies that norm Fn minus Fm p less than 1 by 2. Okay. As per the Cauchy sequence, norm Fn minus Fm under the pth norm less than epsilon. Here epsilon is equal to 1 by 2. So, we have this condition for nm greater or equal to n1. Similarly, suppose another epsilon square of 1 by 2. We can choose a positive integer n2 greater than n1. Okay. In above nm greater or equal to n1. Here we have taken nm greater or equal to n2 and also n2 greater than n1. So, norm Fn minus Fm less than square of half. Okay. In general, n1, n2 and so on nk let nk plus 1 greater than nk be such that less or equal to, here it will be less than norm fn minus fm less than half power k plus 1 for all nm greater or equal to nk plus 1. We claim that the subsequence fn k is equal to 1 to infinity converges almost everywhere to a limit function f belonging to LP. From the construction of f and k, it is evident that summation k is equal to 1 to infinity norm this fn k plus 1 minus fn k under pth norm. Okay, this one. Here it will be the sum limited term here. Okay, so we can take the infinite term here. So in general, we can write summation k is equal to 1 to infinity norm fn k plus 1 minus fn k less or equal to k is equal to 1 to infinity. Okay, so here 1 by 2 power k as per this. Suppose k is equal to 1. Okay, so fn 2 minus fn 1 less than half this, and if k is equal to 2, then we have this term, and so on. We have infinite term. So this is summation k is equal to 1 to infinity 1 upon 2 to the power k. This is the geometric infinite series. Okay, so here common ratio is 1 by 2. So a upon 1 minus r common ratio, first term 1 by 2, common ratio 1 by 2, that is a upon 1 minus r, that is 1. Hence this series is bounded. If we define gk mod fn1 plus mod fn2 minus fn1 plus and so on fnk plus 1 minus fnk for k belonging to n, then gk is an increasing sequence of non-negative measurable function such that norm gkp, taking here integral over x gk integration with respect to the measure mu. So each term this can be written as norm of gkp. Okay, pth norm. So this term also, this taking the norm of both sides of this term under pth norm. Applying the Minkowski inequality. So we have norm gkp. Okay, this is norm fn1 p plus norm of this term, that is summation I is equal to 1 to k norm fn I plus 1 minus fn I, where I is equal to 1 to k. Okay, so by equation this one, we have norm gk is equal to norm fn1 plus 1. Okay, fn1 integrable over x fn1 power p d mu less than infinity, here also 1. So total quantity is less than infinity. Okay, that is norm gkp is bounded. Let limit k tend to infinity gk is equal to g. Okay, converges to the point g. Then by the monotone convergence theorem and the above estimate of gkp, we have limit k tend to infinity integral mod gkp d mu equal to mod g power p d mu, which is bounded by this assumption. Hence, g belonging to LP, that is norm GKP is this. So, integral mod fn1 summation I is equal to 1 to infinity f n I plus 1 minus fn I whole power p, okay, as per this, d mu less than infinity, okay. It follows that this one bounded almost everywhere. And so the series summation this converges almost everywhere. See, this one is less than infinity almost everywhere, then and so the series this also converges almost everywhere, and consequently the series fn1 x plus summation I is equal to 1 to infinity fn I plus 1 x minus gn I x, because this is converges, fn I converges to gn I, okay, converges almost everywhere. The kth partial sum of this series fnk plus 1 x, and so the sequence fnk, where k is equal to 1 to infinity, converges to a complex number fx for all x belonging to A, where A is measurable and mu A dash is equal to 0. Define fx is equal to 0 for all x belonging to A dash. It is easy to see that f is measurable and complex valued on x. We will now show that f is the limit in LP of the sequence fn. Let epsilon greater than 0 choose L so large that S t greater or equal to NL. This implies that norm Fs minus Ft under pth norm less than epsilon. This is possible since Fn is a Cauchy sequence, okay. So we can write, because Fn is Cauchy sequence. Then for k greater or equal to L and m greater than NL, we have norm Fm minus Fnk under pth norm less than epsilon. This implies that, as per the statement, we can write integral mod Fm minus Fnk power p d mu whole power 1 by p less than epsilon. This implies that mod Fm minus Fnk power p d mu less than epsilon power p, taking the pth power of both sides. Using the Fatau lemma. What is the Fatau lemma? Let Fn be a sequence of non-negative measurable functions. Integral limit n tend to infinity infimum of Fn d mu less or equal to limit n tend to infinity infimum of integral Fn d mu. Okay. Using this result, we have here mod f minus Fm power p dx. Okay, Fnk converges to the point f. So, integral mod f minus Fm power p dx is equal to integral k tend to infinity limit mod Fnk minus Fm power p dx less than epsilon power p. Thus, for each m greater than NL, the function f minus Fm is in LP. And so, f can be written as f minus Fm plus Fm. This is also in LP. And limit n tend to infinity norm f minus Fn under pth norm equal to 0. That is, norm f minus Fn p converges to 0 as n tend to infinity. Thus, F is the limit in LP of the sequence Fn. Hence, LP is complete. In this lecture, we have discussed the LP spaces as Banach spaces. These are the references which have been used in this lecture. Function analysis, Dover publication, written by George Beckman and Lawrence Naresy. Introductory function analysis with applications, John Whaley and Sons, written by Erwin Krejcik. Function analysis, New Age International Publisher, written by V.V. Lemieux and other. Function analysis, Tata McGraw-Hill, written by Walter Rodin. Thank you for your attention.